Welcome! In this video, we will explore LeetCode problem number 883, projection area of 3D shapes. We'll break down the problem, discuss various approaches, and provide an efficient solution. Stick around to learn key concepts and improve your problem-solving skills. In this problem, you're given an NXN grid where each cell represents the height of a 3D shape at that position. The goal is to calculate the total projection area of the 3D shape, which is the sum of three different projections. First, the top-down projection area counts how many cells in the grid are not empty, meaning their value is greater than 0. Second, the front projection area is determined by finding the maximum height in each row of the grid. Lastly, the side projection area is calculated by finding the maximum height in each column. Combining these three components gives the total projection area of the 3D shape. The input consists of the size of the grid, n, and the 2D array grid where each value represents the height at that specific cell. The output is a single integer representing the total projection area. Consider the first example where the input grid is 1, 2, 3, 4. To calculate the top-down projection area, we count all the cells with non-zero values. Since all the cells in this grid are non-zero, the top-down projection area is 4. Next, for the front projection area, we take the maximum value from each row. The maximum of the first row is max, 1, 2, equals 2, and the maximum of the second row is max, 3, 4, equals 4, so the front projection area is 2 plus 4 equals 6. For the side projection area, we look at the columns. The maximum of the first column is max, 1, 3, equals 3, and the maximum of the second column is max, 2, 4, equals 4, giving a side projection area of 3 plus 4 equals 7. Adding these together, the total projection area is 4 plus 6 plus 7 equals 17. Now let's look at the second example where the grid is 2. Since there's only one cell, the top-down projection area is simply 1 because there's one non-zero cell. For the front projection area, the maximum value in the single row is max, 2, equals 2. Similarly, for the side projection area, the maximum value in the single column is also max, 2, equals 2. Adding these values, the total projection area becomes 1 plus 2 equals 5. Finally, consider the third example where the grid is 1, 0, 0, 2. First, the top-down projection area is calculated by counting the non-zero cells, which are 1 and 2, giving a count of 2. For the front projection area, we find the maximum value in each row. The maximum of the first row is max, 1, 0, equals 1, and the maximum of the second row is max, 0, 2, equals 2, resulting in 1 plus 2 equals 3. For the side projection area, we find the maximum value in each column. The maximum of the first column is max, 1, 0, equals 1, and the maximum of the second column is max, 0, 2, equals 2, giving another 1 plus 2 equals 3. Adding these together, the total projection area is 2 plus 3 equals 8. The problem also specifies constraints, such as the grid size being up to 50 by 50 and all values being between 0 and 50, and highlights edge cases where grids contain only zeros or only one cell, ensuring all calculations are handled correctly. To solve problem number 883, we need to calculate the total projection area of a 3D shape represented by an NXN grid. The projection area consists of three components: the top view, the front view, and the side view. The top view is determined by counting all grid cells where the height is greater than 0. For the front view, we calculate the maximum height in each row, and for the side view, we calculate the maximum height in each column. The total projection area is simply the sum of these three components. Now, one straightforward way to compute this is using a brute force approach. In this method, we iterate through the grid multiple times, once to count non-zero cells for the top view, once to find the maximum height of each row for the front view, and once to find the maximum height of each column for the side view. This results in a time complexity of n squared, which is acceptable because we have to visit every cell at least once. However, this method involves redundant computations, as we revisit the grid for each projection calculation. Instead of using the brute force approach, we can optimize the solution by calculating all three projections in a single pass through the grid. As we iterate through the grid, we simultaneously keep track of the maximum value in each row for the front view, the maximum value in each column for the side view, and the count of non-zero cells for the top view. This eliminates the need for separate passes and reduces redundancy. The time complexity remains O(n squared), as we still need to visit each cell, but the constant factors are reduced, making this approach more efficient in practice. The optimized solution is both straightforward and effective, as it simplifies the implementation while maintaining the same asymptotic complexity. The optimized approach works so well because all three projections can be calculated simultaneously in a single loop over the grid. The top view is calculated by simply counting non-zero cells as we traverse the grid. For the front view, we maintain a running maximum for each row, and for the side view, we maintain a running maximum for each column. This insight significantly reduces unnecessary iterations. Compared to the brute force method, this approach is cleaner and faster, especially for larger grids. While the brute force approach is easy to understand and implement, its redundant computations make it less suitable for larger inputs. The optimized single-pass approach, though slightly more complex, is the better choice for grids of any size, as it minimizes overhead while achieving the same result. In terms of complexity, the optimized single-pass approach achieves a time complexity of O(n squared), since we still need to traverse the entire grid. The space complexity is O(n), as we may need to store maximum values for each column during the computation. However, this additional space is negligible compared to the input size. Here's the Python implementation of the optimized approach. We initialize variables for the top, front, and side views. Then, as we iterate through the grid, we update these values in a single loop. Specifically, we count non-zero cells for the top view, update the row-wise maximum for the front view, and update the column-wise maximum for the side view. Finally, we return the sum of these three components. This implementation is efficient, concise, and adheres to the optimized strategy we just discussed. In problem number 883, our goal is to calculate the total projection area of a 3D shape represented on an nxn grid. Each cell in the grid has a height value, and the projection area is determined by looking at the shape from three perspectives: the top, the front, and the side. The top view simply counts all cells where the height is greater than 0. For the front view, we consider the maximum height in each row, as this reflects the tallest part of the shape visible when viewed from the front. Similarly, for the side view, we look at the maximum height in each column, representing the tallest sections visible from the side. To calculate the total projection area, we sum the contributions from these three views. Let's break this down into a sequence of clear steps, starting with how the grid is represented and the variables we need to initialize. We begin by understanding the grid representation. The input grid is a 2D list where grid I, j represents the height of the shape at position I, j. Since the grid is square, its dimensions are nxn. To calculate the areas, we initialize three variables: top_area to count non-zero cells for the top view, front_area for the sum of maximum heights in each row, and side_area for the sum of maximum heights in each column. The first step in the algorithm is to calculate the top view area. We traverse the entire grid, and for every cell that has a height greater than 0, we increment top_area. Next, we calculate the front view area by iterating through each row. For each row, we find the maximum height using Python's max function and add it to front_area. Finally, for the side view area, we calculate the maximum height in each column. By iterating through all rows for each column, we track the maximum value and add it to side_area. Once these calculations are complete, we sum the three areas top_area, front_area, and side_area to get the total projection area, which we return as the result. Now let's explore the reasoning behind separating the calculations for each view. Each view, top, front, and side, represents a distinct perspective of the 3D shape, and the projection area for each is computed differently. The top view is essentially the count of non-zero cells in the grid. Every cell with grid I, j, 0 contributes 1 unit to the projection area. For the front and side views, we rely on the maximum heights. The front view considers the tallest value in each row, while the side view looks at the tallest value in each column. This approach ensures that we accurately capture what is visible from these perspectives. The algorithm achieves an efficient time complexity of O(n squared), as we traverse the grid once for the top view, and then compute row and column maxima with separate loops. This ensures we process every cell methodically without unnecessary repetition, making the algorithm both clear and performant. To implement this, we rely on simple data structures. The input grid is stored as a 2D list or array of integers, providing straightforward access to elements using indices. For our calculations, we use three integer variables top_area, front_area, and side_area to store intermediate results for the respective projection areas. Let's also analyze the algorithm's efficiency. The time complexity is O(n squared), as we traverse the entire nxn grid to compute the top view. Additionally, finding the maximum in each row and column requires O(n) operations for each row and column, respectively, resulting in another O(n squared). As for space complexity, the algorithm operates directly on the input grid and uses only a fixed number of integer variables, requiring O(1) additional space. This makes the solution efficient in both time and memory usage. Let's address some important edge cases. First, if the grid is empty or has dimensions 0x0, the total projection area is naturally 0, as there are no cells to contribute. For grids with uniform heights, where every cell has the same non-zero value, the top view will count all n-2 cells, while the front and side views will each sum the height multiplied by n. On the other hand, if all cells have a height of 0, all three projection areas will contribute 0, resulting in a total projection area of 0. Now, let's look at the implementation of the algorithm. We start by defining the function projection area that takes the input grid. The variable n is initialized to store the grid's dimension, and we initialize top_area, front_area, and side_area to 0. Then, we loop through each row to compute the top and front areas simultaneously. Within the row loop, we initialize max_o to track the tallest height in the current row. For each cell in the row, if the height is greater than 0, we increment top_area to account for the top view. Simultaneously, we update max_o to ensure it holds the maximum value of the row. After processing all cells in the row, we add max_o to front_area. Next, to calculate the side view, we loop through each column. We initialize max_call to track the maximum height in the column and iterate through all rows to update max_call with the tallest value. After processing all rows for a column, we add max_call to side_area. Finally, we return the total projection area as the sum of top_area, front_area, and side_area. This implementation is clean, efficient, and handles all edge cases effectively. This implementation calculates the total projection area of the 3D shape represented by the grid in three parts: top view, front view, and side view. Explanation of the code. 1. Initialization. The function starts by determining the size of the grid, n, which is assumed to be square, nxn. 2. Top view calculation. The top view projection is calculated by iterating through every cell in the grid and counting the number of cells with a height greater than 0. This is done using a nested generator expression inside the sum function. 3. Front view calculation. The front view projection is obtained by taking the maximum value in each row, representing the tallest column in that row when viewed from the front. This is computed using another generator expression that iterates over each row and applies the max function. For a side view calculation, the side view projection is calculated by taking the maximum value in each column. Here, we iterate over columns, using j as the column index, and for each column, find the maximum value across all rows, I, which represents the tallest column when viewed from the side. 5. Summing up. Finally, the total projection area is obtained by summing the results of the top, front, and side views. Efficiency. This approach is efficient with a time complexity of O(n squared), because we traverse the grid multiple times, once for the top view and twice for the front and side views. Since the grid is small, usually up to 50 by 50 in competitive programming, this solution is optimal and runs efficiently within the constraints. Edge cases. If the grid is empty or contains only zeros, the function correctly returns 0. Handles non-square grids gracefully by working directly on the given dimensions, though LeetCode guarantees square grids for this problem. This concise implementation ensures clarity while adhering to the constraints and requirements of the problem. Here, we start by defining the function projection area, which takes a 2D grid as input. The first step is to calculate the top view projection. This is done by iterating through every cell in the grid and counting all cells where the height is greater than 0. Essentially, this gives us the number of visible cells when looking down from above. Next, we calculate the front view projection, which is determined by finding the maximum height in each row of the grid. For this, we iterate through each row, keep track of the highest value within that row, and then add it to the total front view projection. This ensures that we capture the tallest block visible when looking at the grid from the front. Now, to calculate the side view projection, we focus on the columns instead of the rows. For each column, we determine the maximum value by iterating through all rows at the same column index. This gives us the tallest block visible when viewing the grid from the side. We add these maximum values from all columns to the side view projection. Finally, to get the total projection area, we sum up the top view, front view, and side view projections and return the result. This approach ensures that all three projections are calculated efficiently, giving us the overall projection area of the 3D shapes represented in the grid. To solve this problem, we start by calculating the projection area for the given grid. First, let's look at the top view projection. The top view simply counts all the cells in the grid where the height is greater than 0. For this input grid, we examine each cell. In the first row, we see that both 1 and 2 are greater than 0, so we count 2 cells. In the second row, both 3 and 4 are also greater than 0, adding 2 more cells. This gives us a total of 4 cells with non-zero height. Therefore, the top view projection is 4. Next, we calculate the front view projection, which considers the maximum height in each row. In the first row, the maximum of 1 and 2 is 2. In the second row, the maximum of 3 and 4 is 4. Adding these maximums together, we get 2 plus 4, which equals 6. So, the front view projection is 6. Now we move on to the side view projection, which considers the maximum height in each column. For the first column, we compare the values 1 and 3, and the maximum is 3. In the second column, we compare 2 and 4, and the maximum is 4. Adding these maximums together, we get 3 plus 4, which equals 7. So, the side view projection is 7. Finally, we sum up all the projections to find the total projection area. Adding the top view, front view, and side view projections, we have 4 plus 6 plus 7, which equals 17. Therefore, the total projection area for this grid is 17. For this next example, we're working with a uniform grid where every cell has the same height. Let's start with the top view projection. Since all the cells in the grid have non-zero heights, we count all 4 cells. This gives us a top view projection of 4. Next, we calculate the front view projection by finding the maximum height in each row. In the first row, the maximum of 2 and 2 is 2. In the second row, the maximum of 2 and 2 is also 2. Adding these values together, we have 2 plus 2, which equals 4. So, the front view projection is 4. Moving to the side view projection, we find the maximum height in each column. For the first column, the maximum of 2 and 2 is 2. For the second column, the maximum of 2 and 2 is also 2. Adding these values together, we get 2 plus 2, which equals 4. So, the side view projection is 4. Now that we have all 3 projections for this example, we calculate the total projection area. Adding the top view, front view, and side view projections, we have 4 plus 4 plus 4, which equals 12. Therefore, the total projection area for this uniform grid is 12. Let's consider a third example where the grid is sparse, meaning some cells have 0 height. For the top view projection, we count all the cells with non-zero heights. In this grid, only one cell, which is 5, is greater than 0. This gives us a total of 1 cell with non-zero height, so the top view projection is 1. Next, we calculate the front view projection for the sparse grid. For the first row, the maximum of 0 and 0 is 0. For the second row, the maximum of 0 and 5 is 5. Adding these values together, we get 0 plus 5, which equals 5. So, the front view projection is 5. For the side view projection, we look at the maximum height in each column. In the first column, the maximum of 0 and 0 is 0. In the second column, the maximum of 0 and 5 is 5. Adding these values together, we get 0 plus 5, which equals 5. So, the side view projection is 5. Finally, we calculate the total projection area by adding the top view, front view, and side view projections. Adding 1, 5, and 5, we get 11. Therefore, the total projection area for this sparse grid is 11. To analyze the time complexity of this problem, we need to break it down based on the three projections we need to calculate: the top view, front view, and side view. Starting with the top view, we iterate through every cell in the nxn grid to count how many cells have a height greater than 0. Since there are n rows and n columns, the total number of cells in the grid is n squared. Each of these cells needs to be checked, so the time complexity for this step is n squared. Next, for the front view, we calculate the maximum value in each row. With n rows and n elements in each row, the maximum of one row requires n time. Since we repeat this for all n rows, the time complexity for the front view is also n squared. Now, for the side view, we calculate the maximum value in each column. Similar to the front view, there are n columns, and for each column, we iterate through the n rows to find the maximum value. This requires n time per column, and within columns, the total time complexity for the side view becomes n multiplied by n, which is n squared. When we combine the time complexities of all three projections, n squared for the top view, n squared for the front view, and n squared for the side view, we see that the overall time complexity remains n squared. Now let's consider the space complexity of the solution. For the top view, no additional space is required beyond the input grid since we only need to check each cell directly. For the front view, no extra space is needed either, apart from variables to store intermediate results like the current maximum value in a row. Similarly, for the side view, we calculate the maximum value for each column without using additional storage. This is achieved through a single loop that operates on the input grid. Therefore, the overall space complexity is constant, or 1, as it does not depend on the grid size. When comparing the optimized approach to a naive solution, the differences become clear. The naive approach might involve explicitly constructing separate 2D arrays for each projection, one for the top view, one for the front view, and one for the side view. This would require additional storage proportional to the grid size, resulting in a space complexity of n squared. In contrast, the optimized approach avoids these auxiliary arrays entirely and calculates the projections directly, reducing the space complexity to 1. For time complexity, both solutions involve iterating through all rows and columns, so the time complexity remains n squared in both cases. However, the optimized approach is cleaner and avoids the overhead of creating and managing extra data structures. In terms of best, average, and worst cases, the time complexity is consistently n squared, because the algorithm always needs to process every cell in the grid, regardless of the grid's content. Finally, let's solidify the reasoning behind the time and space complexity using big O notation. To compute the top, front, and side projections, we iterate over the entire nxn grid row by row or column by column. Each complete iteration over the grid contributes n squared operations, and since the three projections are computed independently, their costs simply add up linearly. Therefore, the overall time complexity is n squared. Additionally, the solution does not allocate any memory proportional to the grid size. All calculations are performed in place, with only a constant amount of extra space used for variables, resulting in 1 space complexity. This efficiency ensures the algorithm is both time and space optimal for this problem. When tackling the problem, there are a few common mistakes that can lead to incorrect results. First, when calculating the top view projection, it's essential to only count grid cells with a height greater than 0. A common error is counting all cells, even those with 0 height, which inflates the projection area. Next, it's easy to confuse row-wise maximums, which are needed for the side view, with column-wise maximums, which are used for the front view. Since each projection is calculated differently, mixing them up results in incorrect outputs. Another issue arises from hard-coding the grid size, for example, assuming a fixed 3 by 3 grid. Since the problem specifies an nxn grid of any size, hardcoding prevents your solution from handling larger or smaller grids, leading to failures on dynamic test cases. Another mistake to watch out for is inefficient iteration. Recalculating row-wise and column-wise maximums multiple times adds unnecessary complexity, slowing down your code. Instead, pre-computing these values can save time and improve efficiency. Additionally, neglecting to account for edge cases can cause failures. For instance, grids with all zeros or single-cell grids are common test cases, and overlooking them can lead to runtime errors or unexpected results. Handling these scenarios properly ensures your solution is robust and reliable. To excel in interviews, it's important to approach this problem methodically. Start by breaking it down. Explain the three projections, top and side, and front, and how they relate to the grid structure. This shows clear thinking and problem-solving skills. Efficiency is another key point to highlight. The solution has a time complexity of O(n squared), which is optimal because every grid cell must be visited in the worst case. Be sure to also discuss edge cases, such as when n equals 1, grids with all zero heights, or very large grids with uniform heights. Lastly, recognize that this problem is part of a broader pattern of matrix traversal, which is a fundamental concept in grid-based problems. Identifying this connection demonstrates a deep understanding of similar challenges. This problem shares similarities with other grid-based problems on LeetCode. For example, LeetCode 807, Max Increase to Keep City Skyline, also involves working with row and column maximums for grid transformations. LeetCode 598, Range Addition 2, focuses on grid manipulation through cumulative updates. LeetCode 36, Valid Sudoku, is another grid traversal problem, although it's more logic-intensive. Finally, LeetCode 48, Rotate Image, involves matrix rotation and is a great exercise for practicing grid transformations. When thinking about alternative approaches, one option is using a single iteration with helper arrays to store row and column maximums. This reduces redundant calculations, making the solution more efficient, though the code can become slightly more complex. On the other hand, a brute force approach, where the top and side and front views are computed separately with nested loops, is easier to implement but less efficient for larger grids due to redundant iterations. While exploring solutions, you may come across the idea of using recursion to compute maximum values for rows and columns. However, this approach is not recommended. Recursion overcomplicates an otherwise straightforward problem and offers no performance benefits. Iterative solutions are not only more efficient but also much more readable, making them the better choice for this problem. Keeping your approach simple and clear will help you avoid unnecessary complexity and ensure optimal performance. Great job! We've successfully solved LeetCode problem number 883 and learned how to calculate projection areas of 3D shapes. Remember to practice similar problems to strengthen your grid manipulation skills. Don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!